On November 18th, 2026, at exactly 2:16 in the morning, a human creation will quietly cross a physical threshold we have never reached before. That creation is Voyager 1. Moving at 38,000 miles per hour, it has been traveling outward through the dark for nearly 50 years without stopping. Even after half a century of travel, Voyager will only be one light day from Earth. That represents the distance light covers in a single 24-hour period. If 50 years of our best engineering equals only 24 hours of light's natural speed, humanity is moving at a microscopic crawl compared to the scale of the universe. To understand why, we have to look at how fast light actually moves. In a vacuum, it covers roughly 186,000 miles every single second. Humanity first calculated this in 1676. Ole Romer noticed Jupiter's moons appearing slightly off schedule depending on Earth's position. He realized the discrepancy was the time light needed to cross the extra distance between the two planets. Inside our immediate neighborhood, that speed feels staggering. Light hits the moon in 1.3 seconds, and it reaches the sun in 8 minutes and 20 seconds. This is the absolute speed limit of the universe. A light year is a unit of distance, a staggering physical gap of 5.88 trillion miles. This timeline illustrates the distance for current technology. Voyager would need 18,000 years to cross a single light year. To reach Proxima Centauri, the nearest star, the journey extends to 73,000 years. Nobody in the next 1,000 generations would see it arrive. The true outer boundary of our solar system is the Oort cloud, a spherical shell of icy debris, extending up to 2 full light-years from the Sun. Mapping a 1 light-year journey against this structure reveals the scale of our isolation. Even if we could travel a full light-year from Earth, we would technically still be sitting in our solar system's driveway. Why don't we simply engineer something faster to close the gap? We have tried. The Parker Solar Probe is the fastest object humanity has ever built, peaking at 430,000 miles per hour. But Parker achieves this by using the Sun's gravity in a locked orbit. It is anchored to our star, incapable of heading toward another system. The central engineering bottleneck is the fuel-to-mass ratio. To go faster, you need more fuel, but fuel adds mass, requiring even more fuel. This relationship grows exponentially, making conventional rockets impossible. Furthermore, every gram of fuel used to accelerate must be matched to decelerate. Conventional propulsion has hit an unyielding wall of physics. We are facing a ceiling that current technology cannot push through. The light year represents a physical fact about the gap between what we can build and where we want to go. Voyager 1 took a famous photograph looking back at home from deep space. Carl Sagan noted that every human triumph and tragedy in the history of our species lived out their lives on a mote of dust suspended in a sunbeam. These incomprehensible distances frame our entire world as a lonely speck in an overwhelming cosmic dark. This leaves us with a choice. We can look at these impossible distances and decide the effort isn't worth it, or we can keep reaching. Engineers refuse to stop, dreaming up radical concepts like laser sails and nuclear pulse propulsion to cheat the rocket equation. Even with theoretical technology, a journey of a few centuries is an act of throwing a bottle into the ocean, knowing we will never personally see it reach the shore. While we cannot cross a light year yet, the stubborn, relentless act of trying is the most fundamentally human thing we can do.